not these in midterm 2. Lagrange multipliers. Okay. So what is the story of Lagrange multipliers? Lagrange multiplier comes with a goal function and objective function. So these problems, what is given? Is one, a goal or objective function. That's the function that you're optimizing. 2 is a constraint or constraints. Constraint. So 2 things are given. There are, one thing is that, and here's the thing, if we're giving you the problem, very much likely that the domain is closed and bounded, or through experience, we know that either minimum or maximum or both of them exist. So that requires another level. To know that through the experience, we know that minimum and maximum and everything exists. So you don't need to check any of the things that you check over there, basically. That we're testing you just in your skills of finding the Lagrange multipliers. So how does this work? If all the nice properties are satisfied, there is a continuity and continuity of second derivatives and that sort of things. Then what you need to do, let's call this F, call this either G, and if there are more than one constraint, you go G and H. Then you want to set, if you only have G, you set gradient of F equal to lambda gradient of G. And then you add, this would give you a few equations. And then you set G equal to G of, let's say, X, Y, and Z, or X, Y equal to constant that is given. That gives you one equation. Get rid of lambda first if you can. And solve for X, Y, and Z. Then the maximum output, F of X and Y and Z, is the max. And the minimum output is the min. So that's the story. And then I'll tell you what happens if I have more than one constraint. So far, any questions? Are we doing okay? So, let's do this question. This one is, again, one of those questions that I know. It says cardboard box without a lid is to have a volume of that much. Find the dimension and minimizes the amount of cardboard used in there, right? So through the experience, I know that the minimum can be achieved in here. What do I do? Here, I use the Lagrange multipliers. Let's use 1. I have to figure out my objective function. And I have to find the Lagrange multipliers. objective function, what am I trying to optimize? I'm trying to optimize the amount of cardboard used, right? The amount of cardboard. By the way, the cyan color is okay for the Zoom also, right?
Yes.
Okay, thank you so much for answering. And am I recording? My obsessive compulsive behavior is
Yes,
just,
you are.
I am.
Yeah.
Okay, thank you. Okay, yeah, I am. There we go. And then what is the, oh, sorry. This meant, I meant to say constraint. So the constraint is what limitation we have. What limitation we have? We have to have the volume equal to 32 cubic inches. So that's the constant volume. So let's put this in words. The amount of cardboard used, how do I find it? Let's draw the picture. It's supposed to be a cardboard box and without a lid. So no lid on top. So this one is basically, I can see inside the cardboard, but I have all four sides. Let's say, let's have this X, let's have this Y, let's have this Z. This side and that side are equal, then this side and that side are equal in size, and the bottom is X times Y. So if I want to write down the amount of material used, it's going to be X times Y in the bottom, and 2Y times Z plus 2 times X times Z. Okay, now, yeah, that's correct. And now constant volume means that X times Y times Z is equal to the value given. Now, this part is called G of X and Y and Z, and that's the constant C. That's the constraint, right? So that's how it goes. Now, first thing I want to find is gradient of F, then we want to find gradient of G. Gradient of F is going to be this function. So hold on. Guys, never forget gradients and two more things that we were teaching, either taught on Friday or we're teaching on Monday. That's called divergence and curve. Those are forever with you. So gradient of F is this, right? Partial with respect to X and Y and Z, and it's a vector. Partial with respect to X of that is Y. With respect to X of that is 0. With respect to X of that is 2Z. Partial with respect to Y of that is X. With respect to Y of that is 2Z. In respect to Y of that is 0. Partial respect to Z of that is 0. With respect to Z of that is 2Y. With respect to Z of that is 2X. Now, same thing for G. G only has one term. And here, oh, there's an equal sign missing here. I'm sorry. There we go. With respect to X of XYZ is going to be YZ. Right? Y and Z are constant times X. With respect to Y of XYZ is going to be XZ. With respect to Z of XYZ is going to be XY. Now, what you want to do is to set gradient of F equal to lambda gradient of G, and that gives you 3 equations. Okay. So what are those three equations? The first component of f, gradient of f equal to lambda times the first component of gradient of g. That's the first one. So it's y plus 2z equal to lambda yz. Then the first term in here is equal to lambda times the first term. Sorry. The second component of gradient of f is equal to lambda times the second component of gradient of g, which is x plus 2z equal to lambda xz. Then there is a third one, 2x plus 2y plus 2x equal to lambda x times y. Then you remember I have x, y, z, and lambda, but only three equations. So I need one more. What is that other equation? That's your constraint. So your constraint goes among those equations as well. Okay. Now, my first goal is to get rid of lambda if I can, and get two equations out of this if possible. So what do? One of the easy ways, there's another method that is used in the solutions. And this one actually is more methodical than the other one, but that one is a fun method to use, basically. So you want to look at that too. Here, I get lambda, solve for lambda, I get y plus 2z equal to yz. Here I solve for lambda, and I get x plus 2z over xz. Here I solve for lambda, and I get 2y plus 2x over xy. Now what do? I eliminate lambda between these two. Y plus 2z over yz equal to x plus 2z over xz. I don't know, you call it cross, do whatever you can. By the way, since we have a cardboard, I know x, y, z cannot be 0, so I can get rid of this one. See, right? And then cross multiply to get xy plus 2xz equal to xy plus 2yz. And then subtract the xy from both sides. Get 2xz is equal to 2yz. And that gives me what? X equal to y? So this entire story came from that. Now I probably want one more equation. So I have x equal to y as one of my as the result of eliminating lambda. Let's do the same thing with these two. And if I do that, I get x plus 2z over xz equal to 2y plus 2x over xy. And then x simplifies from both sides, multiply them through. And then hold on. Let me check my work very quickly. And so I have 2yz simplify from both sides. And after that, x simplifies to get y is equal to 2z. So I got my two equations out of the three equations by eliminating lambda. Now I have these two and that one. And that is going to be, hopefully this white is going to work. Sometimes the white pages don't work very well. So let me know if you can't see it. So in here, I have x equal to y equal to 2z, and x, y, z equal to 32. And so plugging back in, I can replace y with 2z. I can replace x with 2z in here. And it would be 2z, 2z, z equal to 32. That is 4z to power 3 equal to 32. That's z to power 3 is equal to 8. So z equal to 2. Using those two, I get x equal to y equal to 4. So the only points that I found is going to be 4, 4, and 2. And to find the minimum, so I don't have multiple points, so I don't have to compare the minimum values and maximum values, but I can plug it back into the function. What's the original? Here's the original. So I can plug it back into that original and find the minimum amount of the minimum area of the cardboard. So f of 4, 4, and 2 is equal to 4 times 4 plus 2 times 4 times 2 plus 2 times 4 times 2, which is this 16 times 3? 16 times 3 is the minimum amount of cardboard. Again, this was question that came with the experience that I will achieve a minimum value by the experience. You guys, why are we bringing this up? Because the choices are, if you're using Lagrange multipliers, either closed and bounded domain, or by business experience that there is a minimum value, and other places it gets bigger, or you have to know the shape of the objective function. And so you can kind of guess that there's a minimum or maximum. And sometimes you need to know the shape of both of them, basically. There are numerical methods to do that also, but Lagrange multipliers is used in business a lot. Okay. How are you guys doing? Are you tired of me? Oh, I'm still in page 2. Should I do one more? Maybe just set up, but not solve this time. Sounds good? So